A cosmic alignment so perfect it defies chance, or a deliberate arrival we were never meant to see. On September 12, 2025, astronomers witnessed the impossible. Two colossal objects arriving from opposite ends of the universe, set to rendezvous in our solar system during a total observation blackout. The official story is twin comets, but the evidence points to something far stranger. Let's explore this together. Swan's dramatic arrival. What does it look like when the impossible streaks across the sky? On September 12, 2025, we found out. The SWAN instrument, a solar wind anisotropy sensor aboard the SOHO spacecraft, flagged a new object blazing a path through the inner solar system. The first data sets, analyzed by teams led by SOHO project scientist Bernhard Fleck, were staggering. The object possessed a tail stretching nearly 2.5 degrees across the sky, about 5 times the width of a full moon. To put that in perspective, a tail of that magnitude suggests a hydrogen outgassing rate hundreds of times greater than a typical long-period comet. Its initial brightness was clocked at magnitude 7.4, luminous enough to be seen with backyard telescopes from a distance of over 150 million kilometers. This wasn't some faint smudge, this was a spectacle. News ignited across astronomy networks. And just 2 days later, an amateur observer captured a jaw-dropping image showing a streak so immense it barely fit the camera's frame. It was too big, too bright, and its trajectory was already looking far too precise. The raw energy output required to generate such a visible display at that distance was the first red flag that this was something entirely new. Official recognition and growing mystery. A name makes it real but can also deepen the mystery. By September 13th, the International Astronomical Union's Minor Planet Center made it official, designating the object C/2025 R2 or SWAN in honor of the instrument that found it. Within a single weekend, the global astronomy community, from professionals using the Hubble Space Telescope to amateurs in their backyards, was completely fixated on this celestial titan. They traded images and brightness measurements across hemispheres, trying to make sense of its unprecedented behavior. Most comets discovered in the modern era are faint smudges requiring powerful telescopes, but SWAN was a spectacle for anyone who knew where to look. Its magnificent tail sliced through the constellation Virgo at a blistering pace of 20 arc-seconds per minute, growing brighter with each passing day as it raced toward the sun. The conversation quickly shifted from simple observation to intense speculation, with astronomers like Dr. Robert Warwick, the discoverer of Oumuamua, noting the statistical improbability of such a bright object appearing with so little warning. The amateur community, often the first to notice unusual behavior, was already debating what could possibly power a tail this long and this bright. It was simply too big, too vivid, and too fast to be ignored. The cosmic coincidence. Some things are so unlikely they stop looking like a coincidence. C/2025. R2. SWAN is not the only strange visitor this October. Days before, another object, 3I/Atlas, was already inbound from a completely different part of the sky. Imagine a celestial map. SWAN's path traces back from Aquarius while Atlas entered from the direction of Sagittarius. Yet both are set to reach their closest pass by the Sun within the same 10-day window. For Atlas, that's October 17th at a distance of 1.36 AU. For SWAN, it's just 3 days later, around October 20th, at a much closer 1.0 AU. Their perihelion points are separated by only about 50 million kilometers, closer than Mars ever gets to Earth. The geometry is what's truly stunning. Both are on steeply inclined orbits, with SWAN's path tilted more than 60 degrees, and Atlas nearly 90 degrees to the ecliptic plane. As orbital dynamicist Paul Wiegert would tell you, the statistical probability of this kind of synchronized arrival from such different trajectories is infinitesimally small. It's a corridor in space-time that seems to have been deliberately targeted. This is not random chance, it is a rendezvous. Atlas breaks the rules. So what happens when an object refuses to follow the laws of physics as we know them? 3I/Atlas first caught astronomers' attention by breaking all the rules. Early spectrographs from the Atacama Large Millimeter Array reported something that really set off alarms: a body dominated by nickel with virtually no iron, a ratio that's just unheard of in natural celestial objects. This, honestly, contradicts everything we know about comets and asteroids, which almost always contain iron-nickel blends, similar to chondritic meteorites. The claim was so radical, that some labs immediately called for data re-verification. The mystery only deepened when its coma was found to be pumping out carbon dioxide, detected at a strong 4.3 micron spectral line, at rates 5 times higher than water. But what really couldn't be explained was its motion. Observers noted 3 distinct non-gravitational accelerations, each providing a delta V of several meters per second. These weren't the gentle pushes from solar heating, they were sharp, sudden bursts, almost as if the object had fired a thruster. The only other object that showed similar acceleration was Oumuamua, but as Harvard astronomer Avi Loeb pointed out, the pulses from Atlas seemed far more controlled and powerful. Swan, the fortress. If Atlas is a nimble drone, then Swan is a battleship. The scale of C/2025 R2 is, honestly, hard to comprehend, but it's the data that paints a radical picture. One that has driven speculators like Harvard's Avi Loeb to consider similar theories for other objects. It all began with reflectance data. Swan's core has an albedo or reflectivity far higher than a typical dark comet nucleus, matching the signature of polished metal. Some analysts even argue it fits a nickel-cobalt blend, an alloy used for its immense strength. Then came reports of a silvery halo around the nucleus, an anomaly some interpret as a plasma envelope or an electromagnetic shield. This is where it earned the nickname, the Fortress. Unlike Atlas, Swan appears steady and invulnerable, refusing to fragment as it nears the sun. Even its tail shows evidence of micro-thrusts, tiny rhythmic pulses at a consistent frequency that defy natural outgassing. Add in its 22,554-year orbit, and you have an object that appears to be ancient, armored, and on a deliberate, powered course. It isn't just passing through, it's arriving. Mission theories. Coincidence or a coordinated mission? When a long-period object on a 22,554-year cycle and a hyperbolic interstellar object arrive together, the odds of chance really plummet. This has fueled a wave of mission theories. The first, and most routine, is a scheduled refueling run, with the sun acting as a cosmic pit stop for 2 engineered probes. A second, less peaceful theory suggests an intervention or a confrontation, especially given the incredible power levels required for their observed accelerations. A third theory, championed by thinkers like Dr. Avi Loeb, proposes an audit chain. Oumuamua, or 1I/2017 U1, was the first scout, followed by 2I/Borisov, and now Atlas and Swan represent escalating responses to Earth's century of radio transmissions. Each new arrival would be a more complex probe sent to check in. In every scenario, the sun isn't just a backdrop, it's the rendezvous point, the power source, and the beacon. The idea of using a star for a gravitational assist or energy top-up is standard practice for our own probes, like the Parker Solar Probe, making this theory, honestly, chillingly plausible. Ancient connections. An orbit of 22,554 years is, well, a link to a different chapter of human history. The last time Swan would have passed was around 20,000 BCE, right at the peak of the last glacial maximum. This is where the story connects to Göbekli Tepe, a site in Turkey built around 9500 BCE. Researcher Martin Sweatman has proposed a pretty controversial theory that its pillars are actually an astronomical observatory, recording a cataclysmic comet impact that triggered the Younger Dryas climate shift. He argues that Pillar 43 specifically tracks a long-period celestial object. Mainstream archaeologists, including the site's original lead excavator Klaus Schmidt, strongly disputed this, maintaining the carvings are symbolic. Still, the timing is, hard to ignore. If Swan is on a recurring path, its last visit coincided with a transformative period for humanity. Whether that is a coincidence or a clue remains a fiercely debated question. It adds a layer of mythic resonance to an unbelievable event, suggesting we may have seen this visitor before. The blackout window. Just as things get interesting, the lights go out. From October 8th to 18th, both Swan and Atlas will pass through solar conjunction, meaning the sun's glare makes them impossible to observe for optical telescopes on Earth. This affects every major observatory, from the Very Large Telescope in Chile to the Keck Observatory in Hawaii, as the objects will be within a solar elongation angle of fewer than 5 degrees. This is a normal astronomical occurrence, but honestly the timing is incredibly convenient. Rumors are circulating of internal memos from agencies like US Space Command and the European Space Agency, directing teams to suspend high-resolution imaging. Proposals for alternative observation methods have allegedly been denied and raw data requests delayed. A handful of telescope allocation reviewers speaking off the record have described explicit orders to avoid public statements. The result is a forced silence at the exact moment when the two most anomalous visitors in modern history make their closest approach, leaving a frustrating and highly suspicious gap in the data. Underground resistance. When the official channels go dark, the people build their own. The blackout order may have silenced major observatories, but it ignited a firestorm in the amateur and independent astronomy communities. Veteran tracker Bill Gray put out a call to arms across public forums. Keep your scopes on the sky, log everything, and share the raw data on open-source servers. A distributed web of astronomers with powerful 14 and 20-inch telescopes answered. Collectives like the Ibero Tracker Group in Europe began pooling their photometric and astrometric data feeds. Leaks suggest plans to use radio telescopes to pierce the solar glare. This grassroots effort has become the only real-time source for what might happen during the blackout. It's honestly a powerful narrative of decentralized science, a global network ensuring no data disappears. When Swan and Atlas re-emerge, the first images confirming their post-perihelion behavior might come from a garage, not a government lab. This has become a testament to citizen science. Power estimates and implications. Let's talk about the energy, because, wow, the numbers are staggering. The biggest red flag for both objects is the power source required to explain their behavior. If the observed accelerations of Atlas are indeed powered by thrusters, the energy output would need to be on the order of 10 gigawatts. That's the equivalent output of 10 large nuclear power plants like the Palo Verde generating station. But Swan makes that number look insignificant. Based on its size, brightness, and the micro-thrusts detected in its tail, the most extreme estimates place its power output at a mind-boggling 10,000 gigawatts, or 10 terawatts. That is more raw power than the entire energy grid of planet Earth combined. From a physics perspective, as noted by futurists like Dr. Michio Kaku, such energy control would place its creators firmly on the Kardashev scale as a Type 1 or even Type 2 civilization. These figures push the conversation beyond academic debate and into a realm that, honestly, forces us to question everything we thought we knew about our place in the universe. The facts are as clear as they are unnerving. Two anomalous objects, defying all statistical odds, have entered our solar system on a synchronized path. One appears to be a powered drone, the other an armored fortress. They are scheduled for a close encounter during a 10-day window where they will be conveniently hidden from our best telescopes by the sun, accompanied by an official, top-down order for radio silence. This has forced the search for answers into the hands of a global network of citizen scientists. Are we witnessing a cosmic accident, a pre-planned mission, or something else entirely? Whatever the truth is, we are about to find out. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Stellar Tech. The moon, long thought to be a silent, inactive rock, is now revealing secrets that could change everything we know about our closest celestial neighbor. Renowned physicist Michio Kaku has issued a warning after NASA detected a mysterious seismic signal deep within the moon's core. This discovery challenges decades of assumptions and hints at dynamic processes that might even impact Earth over geological timescales. Today, we explore what this seismic activity means for lunar science, future missions, and our understanding of planetary evolution. The moon's hidden activity revealed. For decades, scientists believed the moon was geologically dead, its core solidifying and cooling quietly like a dying ember in space. But recent data from NASA's lunar sensors have detected unexpected seismic pulses emanating from deep within the moon's interior, challenging everything we thought we knew about our celestial companion. These signals suggest the moon's core is not just passively cooling, but undergoing significant changes that could reshape our understanding of lunar evolution. Physicist Michio Kaku has highlighted these findings in recent lectures, warning that the moon's internal activity could have long-term effects on its structure and even Earth's environment over geological timescales. This seismic activity challenges the traditional view of the moon as a static, inert body that finished its geological story billions of years ago. The discovery represents a paradigm shift in lunar science, forcing researchers to reconsider fundamental assumptions about how small planetary bodies evolve and die in our solar system. Inside the moon's dynamic core structure. The moon's internal structure resembles a miniature version of Earth's, with a solid inner core surrounded by a partially molten outer core that scientists are now discovering remains more active than previously thought. New analyses estimate the inner core's radius at approximately 240 kilometers, primarily composed of iron and nickel, enveloped by a fluid outer core extending roughly 350 kilometers from the moon's center. Geological evidence from lunar rocks brought back by Apollo missions shows the moon once possessed a magnetic field generated by its core, similar to Earth's protective magnetosphere. This ancient magnetic field, which existed billions of years ago, gradually faded as the core cooled and solidified. However, recent seismic data suggests the core might still be active in subtle but measurable ways. The core's structure includes a partial melt layer at the base of the lunar mantle, approximately 150 kilometers thick, which sits above the liquid outer core. This complex internal architecture indicates that the moon's interior remains more dynamic than the simple cooling model previously accepted by planetary scientists. Apollo's legacy and modern seismic discoveries. NASA's Apollo missions first placed seismometers on the moon between 1969 and 1977, with the Apollo 11 passive seismic experiment marking humanity's first attempt to listen to another world's internal activity. These instruments detected moonquakes and revealed some internal activity, recording about 100 to 200 meteorite impacts during their operational lifetime and detecting several categories of seismic events. However, the resolution of those 1970s instruments was limited by the technology available at the time. The Apollo seismometers operated until September 1977, providing valuable but incomplete data about lunar seismic activity. Now, with advanced sensors and modern analysis techniques, scientists are uncovering new categories of seismic events that were previously undetectable. These include deep moonquakes caused by tidal forces with Earth, shallow quakes with tectonic origins, and thermal quakes caused by extreme temperature fluctuations between lunar day and night. The new data suggests the moon's interior is more dynamic than once thought, with ongoing processes that continue to shape its internal structure even today. The shrinking moon theory and tectonic activity. One of the most intriguing hypotheses emerging from recent research is that the moon is slowly shrinking as its core continues to cool and solidify over geological time. This gradual contraction causes stress in the brittle lunar crust, leading to the formation of tectonic ridges, fault lines, and surface scarps that are surprisingly young in geological terms. Recent studies have identified hundreds of previously unknown ridges on the moon's surface, some of which may have formed as recently as 200 million years ago, a blink of an eye in geological terms. Using advanced mapping techniques and crater counting methods, scientists determined that these small ridges are younger than other features in their surroundings, meaning the moon's crust is still shifting and evolving today. This slow contraction and associated seismic activity could explain the mysterious seismic pulses detected recently, suggesting the moon is still adjusting internally as it continues its billion-year cooling process. The discovery challenges the long-standing belief that the moon became geologically dormant billions of years ago, and suggests that internal forces are still shaping its surface in measurable ways. Earth-Moon gravitational dance and climate implications. The implications of the moon's internal activity extend far beyond lunar science, potentially affecting Earth's long-term climate stability and orbital dynamics. The moon's gravitational influence stabilizes Earth's axial tilt at 23.5 degrees, which regulates our seasons and prevents chaotic climate swings that would make complex life difficult to sustain. Changes in the moon's mass distribution due to core activity and internal restructuring could subtly affect this crucial gravitational relationship over timescales of millions of years. While these effects are not immediate or catastrophic, they could influence Earth's climate cycles, tidal patterns, and even the Milankovitch cycles that govern ice ages over geological epochs. Michio Kaku has emphasized that the moon acts like a cosmic stabilizer, preventing Earth from wobbling chaotically like other planets of similar size. This stability has allowed for the slow, steady development of ecosystems and eventually human civilization. The moon's gravitational pull creates not just ocean tides, but also slight bulges in Earth's crust, generating heat through friction that contributes to our planet's internal warmth and geologic activity. Next-generation lunar seismic monitoring. NASA is preparing to deploy revolutionary new seismic instruments on the moon as part of upcoming Artemis missions, representing a quantum leap forward in our ability to monitor lunar internal activity. The Farside Seismic Suite, scheduled to land in Schrödinger Basin around 2026, will be the first seismic station placed on the moon's far side since the Apollo era. These next-generation seismometers will be approximately 30 times more sensitive than Apollo-era equipment, capable of detecting ground motions smaller than a single hydrogen atom. The Very Broadband Seismometer, originally designed for Mars InSight mission, represents the most sensitive seismometer ever built for space exploration. Additionally, the Lunar Environment Monitoring Station will establish a long-duration seismic station near the South Pole, where NASA's Artemis missions plan to build a permanent human presence. Unlike Apollo instruments that operated for limited periods, these new systems are designed to continuously monitor lunar seismic activity for months or even years, providing unprecedented insights into the moon's internal dynamics. AI revolutionizes Apollo-era data analysis. Artificial intelligence is playing, a crucial role in revolutionizing our understanding of lunar seismic activity by analyzing decades-old Apollo data with unprecedented precision. It's like machine learning algorithms are detecting patterns and anomalies in the original seismic recordings that human analysts missed or dismissed as noise during the 1970s analysis. These sophisticated AI systems can distinguish between genuine lunar activity and instrument artifacts with remarkable accuracy, flagging seismic events that didn't fit expected patterns and were often filtered out as measurement errors decades ago. NASA scientists describe this process as revolutionary, comparing it to having a conversation with someone for 50 years and suddenly realizing you've been missing half of what they've been saying. The AI analysis has revealed entire categories of seismic events occurring beneath the lunar surface that were completely missed by previous analysis techniques. These aren't just minor tremors but signatures of complex processes happening in the moon's core that provide new insights into its internal structure and ongoing geological activity. This technological breakthrough is helping scientists reconstruct a completely new picture of the moon's internal dynamics and the seismic pulse that has drawn Michio Kaku's attention. Lunar exploration safety and future mission planning. So, the discovery of ongoing seismic activity on the moon, well, it really raises some critical safety considerations for future lunar exploration and colonization efforts. Human missions and those mining operations planned near the lunar South Pole, they've got to carefully consider the risks posed by tectonic activity and potential moonquakes that could damage habitats or endanger astronauts. Understanding fault zones and stress patterns is just essential if we want to ensure the safety and stability of lunar habitats and infrastructure. Unlike Earth, the moon's crust doesn't have water circulation to heal cracks naturally, so once we fracture its brittle surface through mining or construction, those fractures could stick around and potentially trigger even larger seismic events. NASA's upcoming seismic networks will be absolutely vital for mapping these geological hazards and guiding mission planning for the Artemis program. The lunar regolith, which is that layer of loose material covering the moon's surface, actually sits atop a pretty complex network of faults and stress zones that could be disturbed by human activity. Future lunar bases are going to be completely dependent on their structural integrity, making seismic monitoring crucial for astronaut safety, and a habitat breach caused by unexpected seismic activity could be catastrophic, exposing crew members to the vacuum of space with very little warning or opportunity for evacuation. A rare cosmic window for scientific discovery. Michio Kaku emphasizes that humanity exists in a rare cosmic window, a fleeting moment in astronomical time when the moon's internal activity is still detectable before it eventually ceases forever. In another billion years or so, the moon's core may freeze solid completely, ending the geological processes we can observe today. This unique opportunity allows scientists to study planetary evolution processes that happen over billions of years, providing insights that, honestly, can't be obtained any other way. The moon is pretty much giving us a live demonstration of how small planetary bodies evolve and eventually become geologically inactive, serving as a sort of natural laboratory for understanding planetary death. Insights gained from studying the moon's core activity can inform our understanding of other rocky bodies in the solar system and beyond, including potentially habitable exoplanets. By watching the moon transition from a molten core to a solid one, scientists gain crucial insights into how different-sized worlds evolve, whether they can maintain protective magnetic fields, and their potential for supporting life. Kaku explains that we're incredibly fortunate to exist at exactly the right moment to witness the final chapters of the moon's geological story. The moon as a key to planetary evolution. The moon's seismic signals represent far more than just scientific curiosities. They're actually fundamental keys to understanding planetary life cycles throughout the universe. As the moon's core continues to cool and solidify, it offers researchers an unprecedented live demonstration of how small planetary bodies evolve and eventually die, providing crucial data for planetary science models. This knowledge is particularly vital as humanity prepares to return to the moon and establish a permanent presence there. Understanding the moon's internal processes helps scientists identify potentially habitable exoplanets and predict how their geological evolution might affect their ability to support life over billions of years. The moon serves as an intermediate step in planetary development, larger than asteroids but smaller than Earth-like planets, giving us really important insights into how different-sized worlds evolve. By studying how the moon's core solidifies and loses its magnetic field, scientists can develop models that predict how long smaller rocky exoplanets might maintain their protective magnetic shields. Michio Kaku's warning reminds us that the moon still holds secrets that could totally reshape our understanding of planetary science, Earth's future, and our place in the cosmic neighborhood. The moon is no longer the silent, dead rock we once thought it was. Thanks to new seismic discoveries and Michio Kaku's warnings, we now know it's a dynamic world with an active interior that could even influence Earth itself. As we prepare to return and explore further, understanding these internal processes is more important than ever before. Stay tuned for more updates on lunar science and the future of space exploration. Thanks for watching Stellar Tech, and don't forget to subscribe for more cosmic insights. What if the first definitive proof of alien technology wasn't a grand arrival, but, just a single ambiguous frame of data on a NASA live feed, visible for only a fraction of a second before the screen went black? This is the story of a hypothetical event, a thought experiment grounded in real science. On June 18th, a NASA feed tracking a fictional interstellar visitor named 3I Atlas suddenly cuts out. But not before revealing something that looks eerily artificial. Was it a simple glitch, or maybe our first glimpse of something engineered? Let's explore this together. The initial discovery. So, how does a story like this even begin? Well, it starts with the silent, relentless work of a real program, the Asteroid Terrestrial Impact Last Alert System, or ATLAS. Funded by NASA and operated by the University of Hawaii, this network of robotic telescopes with key figures like Principal Investigator Larry Deneau at the helm, scans the entire visible sky every 24 hours. Its primary mission is planetary defense, but its wide, fast survey is perfect for catching interstellar interlopers. In our scenario, on July 1, 2025, ATLAS flags an object on a hyperbolic trajectory. This isn't just another rock orbiting our sun. Its path proves it's a visitor from another star system, moving way too fast to be captured by our sun's gravity. After its trajectory is confirmed by the Minor Planet Center, it's designated 3Y Atlas. This would immediately trigger a global astronomical response. Scientists like Karen Meach, who led the characterization team for Oumuamua, would spearhead campaigns to observe the object with every major telescope available. This isn't just about getting a picture, it's a frantic race against time to gather data on a messenger from a distant, unknown solar system before it disappears back into the void forever. The anomalous frame. Here's the moment a routine observation becomes honestly a profound mystery. A public live feed is tracking 3I Atlas. At precisely 0317 and 12 seconds UTC, the feed freezes on a final frame before cutting to black. The image is mostly standard deep space fare, a dim, fuzzy nucleus surrounded by a cloud of gas and dust. But in the lower left quadrant, something is different. There is a razor-sharp glint of reflected sunlight forming a perfectly straight line. This is the kind of anomaly that would make a SETI pioneer like Jill Tarter take notice. Natural objects in space, comets, asteroids, dust clouds, are chaotic and irregular. Light scatters off them in diffuse, uneven patterns. But this glint is geometric. It behaves as if it's reflecting off a polished, flat surface. Independent astronomers running their own analysis software would see their edge detection algorithms flag the segment immediately. It's too consistent, too crisp. In the long search for extraterrestrial intelligence, this is exactly the type of techno-signature researchers look for, an artifact that appears manufactured, standing out starkly against the random backdrop of nature. The question is no longer just what is this comet made of, but was a part of it made at all? Data verification. An image this provocative is, well, worthless if it can't be authenticated. This is where the modern, decentralized nature of science communication becomes critical. In the minutes after the blackout, a global network of independent archivists and citizen scientists would swing into action. They run automated scripts that continuously record public NASA feeds. Packet captures of the 3i Atlas feed from servers in Germany, Australia, and the United States would be uploaded to multiple repositories. Each file, time-stamped 0317 and 12 seconds UTC, is protected by a unique cryptographic hash, a long string of characters serving as a digital fingerprint. This concept, with roots in the work of cryptographers like David Chaum, ensures data integrity. When compared, every single archived file matches, bit for bit. The German hash is identical to the Australian hash, which is identical to the original broadcast. This provides undeniable proof that the frame was not altered, manipulated, or a hoax created after the fact. The chain of custody is forensically sound, the evidence is clean. The anomaly, whatever its cause, was genuinely present in the data stream from the spacecraft. This eliminates any possibility of a simple prank and honestly forces the scientific community to confront the data as it is. Technical explanations. Before we entertain alien explanations, we have to exhaust all the mundane ones. So, why did the feed drop? The most probable official reason would be a routine network handover. NASA's deep space communications are a marvel of engineering, managed by experts like those at the Jet Propulsion Laboratory, but they aren't flawless. Signals travel from a spacecraft to a relay satellite in the Tracking and Data Relay Satellite System, or TDRS, then down to one of the 3 deep space network complexes on Earth. As the Earth rotates and satellites move, the signal must be handed off from one station or satellite to another. An engineer like Mark Raymond, known for his work on missions like Dawn, would explain that these handovers can occasionally cause a brief loss of signal. These handover blanks are common, logged, and typically last for a few seconds. They show up as a gap in the data logs with a specific reason code, so a blackout is not in itself a conspiracy. The entire system is built with these brief interruptions in mind. The deeply unsettling part of this scenario isn't the blackout itself, but its timing. A routine technical glitch occurring at the exact nanosecond a potentially paradigm-shifting anomaly appears on screen is a coincidence of astronomical proportions. Digital forensics. Let's put the frame itself under the microscope. Digital forensics is an unemotional discipline, and it offers 2 powerful non-exotic explanations for the straight edge. The first is video compression. To transmit massive amounts of data across millions of miles, images are compressed using algorithms like JPEG or MPEG. These codecs, whose development owes thanks to computer scientists like Ken Perlin for their work on procedural textures and noise, divide an image into an 8x8 pixel grid. When a faint linear feature happens to align with the grid's boundaries, the algorithm can snap it into a perfectly straight line, exaggerating its geometric appearance. It's an artifact of the math, not a feature of the object. The second culprit is a cosmic ray. Space is saturated with high-energy particles that constantly bombard camera sensors. A particle can streak across a sensor's pixels, leaving a bright, and often perfectly straight trail that lasts for only a single frame. This is a well-documented phenomenon. The most likely forensic conclusion would be a double hit. A cosmic ray created a faint streak that was then amplified and sharpened by the compression codec. It's an elegant, logical explanation that fits the evidence without rewriting any textbooks. But it can't entirely rule out that it was a real object that was simply processed by the same algorithms. 3i Atlas background. To grasp the full weight of this anomaly, we need to remember the real interstellar objects that preceded our fictional one. First came one Oumuamua in 2017. It was a complete enigma. Small, dark, and highly elongated, it showed no visible coma or outgassing, yet it accelerated away from the sun, as if something were pushing it. This led Harvard astronomer Avi Loeb to famously propose it could be an artifact of extraterrestrial technology, like a solar sail. Then, in 2019 came 2I Borisov. It was a much more familiar sight, looking and behaving like a classic comet with a clear coma and tail, though its chemical composition was unlike anything from our solar system. These two real visitors set the stage perfectly. They proved that interstellar objects are a reality, and that they can be profoundly weird. Oumuamua, in particular, primed the scientific community to be on the lookout for anomalies. It opened the door to seriously considering technological origins. So, when 3I Atlas appears in our scenario with its own bizarre feature, it doesn't happen in a vacuum. It lands directly on the fertile ground of unresolved scientific debate and public fascination that Oumuamua left in its wake, making the stakes infinitely higher. Scientific scrutiny. In science, an extraordinary claim requires extraordinary evidence, a principle famously championed by the great astronomer Carl Sagan. A single ambiguous frame from one instrument is the very definition of not enough evidence. For the artificial edge hypothesis to be taken seriously, it would have to survive a brutal gauntlet of scientific scrutiny. First, the observation must be independently replicated. Different teams using different telescopes, like the Hubble Space Telescope or the Keck Observatory, would need to observe 3Y Atlas and confirm the presence of the same geometric glint. Second, it needs to be a multi-wavelength detection. If the glint appears in visible light, does it also appear in infrared and ultraviolet? Spectral analysis of the glint itself would be crucial. If the light signature matched a known metallic alloy rather than silicate rock or water ice, the claim would gain significant credibility. As it stands in our scenario, the evidence is anecdotal. It sits on the lowest rung of the evidence ladder. Until multiple independent data streams confirm the same anomaly, the overwhelming majority of scientists would rightly remain deeply skeptical and favor a natural or instrumental explanation. The burden of proof is and must be incredibly high. 3 theories. After all the analysis, the scientific community and the public would be left grappling with 3 divergent paths. The first is the most conservative natural phenomena. A leading cometary expert, perhaps someone like Paul W. Chodas from NASA's Center for Near-Earth Object Studies, would argue that what we saw was a glint off a freshly exposed face of ice. Comets are dynamic bodies. As they heat up, jets of gas can erupt, putting immense stress on the nucleus and causing it to fracture. A large, flat piece of ice could easily shear off, and if it catches the sunlight at just the right angle, it would produce a sharp, geometric glint before tumbling away. The second path is the technical glitch theory, a perfect storm of a cosmic ray hitting the sensor in a straight line, which is then exaggerated by the video compression algorithm. It's an illusion born from the interplay of physics and software. But the third path, the one championed by thinkers like Avi Loeb, is the most profound. It posits that the object is not natural at all, that the edge is a real manufactured component of a larger object, a probe, a solar sail, or even a piece of interstellar debris from a civilization long gone. It is a long shot, but it remains a possibility that cannot be disproven with the available data. Broader implications. An event like this, even a fictional one, would transcend the world of astronomy and have profound societal implications. As Seth Shostak of the SETI Institute has often noted, the discovery of potential intelligence would change our perspective on everything. The immediate aftermath would be a firestorm of public debate about data transparency and potential cover-ups. Why did the feed cut out? Who made that decision? This would lead to intense pressure on government agencies like NASA to adopt even more radical open data policies, perhaps mandating decentralized real-time public archives for all raw telemetry. Funding priorities in science could shift overnight. Congress might allocate emergency funding to projects dedicated to the search for techno-signatures. The event also becomes a massive test of global media literacy. How does the public distinguish between credible scientific analysis and wild speculation? For a world watching, the line between healthy skepticism and unbridled wonder would blur, forcing a global conversation about our place in the cosmos and how we prepare for a discovery that could change humanity forever. One single frame could permanently alter how we look at the night sky. The search continues. While our story of 3I Atlas is a thought experiment, the real search it describes is entering a golden age. We are on the cusp of a revolution in astronomy with the imminent full operation of facilities like the Vera C. Rubin Observatory in Chile. With leading scientists like its director Zeljko Ivazic guiding the project, this observatory will conduct an unprecedented survey of the sky, discovering potentially dozens of new interstellar objects every year. This will transform the field from a data-starved science into a data-rich one. Each new visitor will be a data point, a clue from another solar system. Scientists are now actively developing the AI algorithms and observation strategies needed to characterize these objects quickly and efficiently. They are no longer just looking for comets and asteroids, they are actively hunting for anomalies. They are looking for strange light curves, unusual chemical compositions, and most importantly, objects that move in ways that defy our understanding of physics. The search is on, with more powerful tools and a more open mind than ever before. The next visitor is coming, and this time, we will be ready. The unresolved mystery of the 3I Atlas frame, though fictional, perfectly captures the tension between mundane explanation and profound possibility that drives science forward. It forces us to ask how we would react to a truly ambiguous signal from the cosmos, and highlights the absolute necessity of open data, rigorous skepticism, and relentless curiosity. What do you believe is the most compelling explanation for the anomaly and the blackout? Share your theory in the comments section below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the greatest mysteries of our universe. Thanks for watching Stellar Tech. It's difficult for us humans to fully comprehend the enormity of space. We're comfortable in our own cosmic neighborhood, the solar system, and are used to familiar faces like Jupiter, Mars, and of course Earth. But beyond the heliopause lies the cold oblivion of interstellar space. Only 3 confirmed objects have ever crossed this threshold into our domain. These were the famous Oumuamua in 2017, Borisov in 2019, and now 3I/Atlas in 2025, visitors that bring with them both scientific excitement and perhaps even a hint of cosmic fear about what else might be traveling between the stars. Beyond the heliopause, our interstellar visitors. The vast expanse beyond our solar system represents one of the most hostile environments imaginable. A realm where temperatures approach absolute zero, and the nearest stars are separated by trillions of miles of empty void. Yet occasionally, objects from these distant stellar nurseries complete journeys lasting millions of years to visit our cosmic neighborhood. Interstellar space begins beyond the heliopause, approximately 120 astronomical units from the Sun, where our star's solar wind can no longer push back against the interstellar medium. Dr. Alan Stern from the Southwest Research Institute describes this boundary as humanity's cosmic doorstep, beyond which lies the true wilderness of the galaxy. The detection of interstellar visitors requires objects to exhibit hyperbolic orbits, trajectories that prove they're not gravitationally bound to our Sun and must have originated elsewhere. NASA's definition requires orbital eccentricity greater than 1.0 and excess velocity that cannot be explained by gravitational acceleration from solar system bodies. These mathematical signatures distinguish true interstellar objects from long-period comets that merely appear to come from great distances. The rarity of such detections makes each visitor precious, windows into the composition and formation processes of distant planetary systems that we may never reach with conventional spacecraft. The third visitor, 3I/Atlas discovery. January 2nd, 2025 marked a historic day in astronomy when the Atlas Asteroid Survey detected an unusual object that would soon become our third confirmed interstellar visitor. Dr. Larry Deneau from the University of Hawaii was monitoring the automated detection systems when object A11PL3Z appeared in the survey data, moving at an extraordinary velocity that immediately flagged it as anomalous. Unlike typical asteroids that follow predictable elliptical orbits, this object displayed hyperbolic motion characteristic of visitors from interstellar space. Dr. Robert Warwick, the astronomer who discovered both Oumuamua and helped confirm Borisov, led the initial follow-up observations that confirmed the object's interstellar origin. The Minor Planet Center in Cambridge, Massachusetts coordinated rapid confirmation observations from telescopes worldwide, including the Canada-France-Hawaii Telescope and Gemini Observatory. Within 72 hours, enough orbital data had been collected to definitively prove that A11PL3Z was traveling too fast to be gravitationally bound to our solar system. The object's discovery represents a milestone in astronomical detection capabilities, the first interstellar visitor found by automated survey systems rather than manual observation. 3I/Atlas received its final designation after the International Astronomical Union confirmed its interstellar trajectory and cometary activity, making it officially the third known visitor from beyond our solar system. The Atlas Survey System. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, represents a revolutionary approach to sky surveillance, designed primarily to detect potentially hazardous asteroids, but proving equally capable of finding interstellar visitors. Dr. John Tonry from the University of Hawaii leads the project, which operates 4 telescopes across Hawaii and South Africa, continuously scanning the entire visible sky every 24 hours. Each ATLAS telescope uses a 0.5-meter mirror equipped with advanced CCD cameras, capable of detecting objects as faint as magnitude 19.5. The system processes approximately 100 terabytes of data monthly, using sophisticated algorithms to identify moving objects against the background of stars. ATLAS distinguishes itself through rapid cadence observations, taking multiple images of the same sky regions within hours to detect object motion. The discovery of 3I/Atlas validated the system's ability to detect rare phenomena beyond its primary mission. Dr. Deneau noted that the automated nature of ATLAS allows us to catch objects that human observers might miss due to their subtle motion or unusual characteristics. The system's success has prompted NASA to fund expansion to additional sites, creating a global network capable of providing even earlier warnings for both hazardous asteroids and interstellar visitors that might otherwise escape detection. From A11PL3Z to C2025N1, the naming journey. The designation journey of 3I/Atlas really illustrates the complex process astronomers use to classify and name celestial objects. So, initially it was designated A11PL3Z by the Atlas Survey System, but, as its true nature became apparent, the object underwent multiple reclassifications. Dr. Gareth Williams at the Minor Planet Center explained that automated survey systems use temporary alphanumeric codes before official designations are assigned. Once hyperbolic orbital motion was confirmed, the object received the provisional designation C/2025N1, which indicates a comet discovered in the first half of July 2025. The C/prefix denotes a non-periodic comet, while 2025N1 tells us it was the first comet found during the 14th half-month period of that year. As observations revealed clear cometary activity, including coma formation and tail development, the International Astronomical Union assigned the final designation 3I/Atlas. The 3I prefix marks it as the third interstellar object, following 1I/Oumuamua and 2I/Borisov. The Atlas portion honors the survey system that discovered it, following IAU traditions of crediting discoverers. This naming evolution really reflects the careful verification process required to confirm interstellar origin, ensuring that only objects with definitively hyperbolic orbits receive the prestigious EIN designation reserved for visitors from other star systems. A hyperbolic journey at 58 kilometers per second. 3I/Atlas approaches our solar system with a hyperbolic excess velocity of 58 kilometers per second, a speed that definitively proves its interstellar origin and provides clues about its cosmic journey. Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory calculated that this velocity places 3I/Atlas among the fastest interstellar visitors ever detected, suggesting either a recent gravitational encounter with another star, or acceleration from its parent system. The object's trajectory indicates it entered our solar system from the direction of the constellation Lynx, possibly originating from the Vega stellar system, which is about 25 light-years away. Orbital mechanics reveal that 3I/Atlas has been traveling through interstellar space for an estimated 1 to 3 million years before encountering our solar system's gravitational influence. The object's perihelion, its closest approach to the Sun, occurred on October 30, 2025, at a distance of 0.65 astronomical units, which is well within Earth's orbital radius. Dr. Alan Harris from the German Aerospace Center noted that this close solar approach provides optimal conditions for studying the object's composition through spectroscopic analysis and thermal emission observations. The hyperbolic nature of the orbit means 3I/Atlas will never return. After its solar encounter, the object will be gravitationally accelerated by our Sun, eventually reaching speeds exceeding 70 kilometers per second as it exits toward the constellation Draco. Brightness, rotation, and the 29-hour cycle. Photometric observations of 3I/Atlas have revealed a complex 29-hour rotation period that provides crucial insights into the object's shape, composition, and structural integrity. Dr. Alan Fitzsimmons from Queen's University Belfast leads the International Photometry Campaign, coordinating observations from telescopes worldwide to track the object's brightness variations over time. The 29-hour cycle shows magnitude variations of approximately 1.5, which indicates either a highly elongated shape similar to Oumuamua or surface features with dramatically different reflectivity properties. Light curve analysis by Dr. Mikael Granvik from the University of Helsinki suggests the object is likely tumbling rather than rotating around a single axis, which is consistent with an object that has experienced gravitational perturbations or impacts during its interstellar journey. The rotation period is significantly longer than typical solar system comets, which usually rotate every 6 to 12 hours due to outgassing torques. Thermal infrared observations using the Spitzer Space Telescope show that 3I/Atlas maintains surface temperatures consistent with its distance from the Sun, but with unusual temperature distribution patterns that suggest non-uniform surface composition. The object's brightness peaked at approximately magnitude 10 during perihelion, making it visible to experienced amateur astronomers using moderate-sized telescopes, but remaining too faint for naked-eye observation, despite its considerable size. Coma, tail, and cometary activity. Unlike the mysterious Oumuamua, 3I/Atlas displays clear cometary activity which has, provided astronomers with valuable data about its composition and structure. Dr. Matthew Knight from the University of Maryland leads studies of the object's coma, the fuzzy atmosphere of gas and dust surrounding the nucleus as solar heating vaporizes surface materials. The coma began developing when 3I/Atlas reached approximately 2.5 astronomical units from the Sun, initially appearing as a faint envelope around the central nucleus. Spectroscopic analysis by Dr. Michael DeSanti from NASA Goddard Space Flight Center detected emissions from water vapor, carbon monoxide, and hydrogen cyanide, typical signatures of comet sublimation, but with unusual abundance ratios. The object developed a visible tail reaching lengths of 200,000 kilometers as it approached perihelion, composed primarily of dust particles ejected by outgassing. High-resolution imaging from the Hubble Space Telescope revealed the tail's structure shows periodic variations corresponding to the object's rotation, indicating active regions on the nucleus surface. Dr. Jacqueline Keene from Boston University noted that the gas production rate of 3I/Atlas is approximately 10 times higher than expected for its estimated size, suggesting either unusual composition or internal structure. The cometary activity confirms 3I/Atlas as a volatile-rich object that formed in the outer regions of another stellar system, where temperatures were low enough for water and other compounds to condense. Oumuamua versus Borisov versus 3I/Atlas. So let's compare these three confirmed interstellar visitors, Oumuamua, Borisov, and 3I/Atlas. They really present a fascinating study in contrasts, revealing just how diverse the objects traveling between stellar systems can be. Oumuamua, which was discovered by Dr. Robert Warwick back in 2017, is still the most enigmatic of the bunch. It showed no cometary activity, even when it got close to the Sun, and it had this unexplained acceleration and extreme elongation that made it, truly unique among known solar system objects. On the other hand, 2I Borisov, which was found by amateur astronomer Gennady Borisov in 2019, behaved exactly as astronomers expected an interstellar comet would. It developed a classic tail, showed predictable outgassing, and had a composition pretty similar to solar system comets. Then there's 3I/Atlas, which represents something kind of in-between. It displayed clear cometary activity but with some unusual characteristics that set it apart from typical comets. Dr. Stefano Bagnulo from Queen's University Belfast led comparative studies showing that Borisov had carbon monoxide ratios similar to solar system comets, while 3Y Atlas showed significantly different volatile abundances. When it comes to size, estimates put Oumuamua at around 400 meters long, Borisov at roughly 1 kilometer in diameter, and 3Y Atlas at an estimated 5 to 10 kilometers across, making it potentially the largest interstellar visitor we've detected so far. All this suggests that Oumuamua might represent a rare class of objects, while Borisov and 3I Atlas indicate that typical interstellar comets actually share a lot of characteristics with their solar system cousins. A 3 billion 11-year-old traveler. Determining the age of 3I Atlas is, honestly, one of the most challenging aspects of studying interstellar objects. It requires some pretty sophisticated modeling of cosmic weathering processes and orbital dynamics. Dr. Grigory Fedorets from Queen's University Belfast estimated the object's age to be somewhere between 3 and 11 billion years, based on its surface spectroscopic properties, and assumed travel times from nearby stellar systems. That's pretty wild. It means 3I Atlas could be older than Earth itself, having formed during those early epochs of galactic evolution, when star formation rates were way higher than they are today. Now, cosmic ray exposure modeling by Dr. Renu Malhotra from the University of Arizona suggests the surface should show significant radiation damage after billions of years in interstellar space, but interestingly, observations indicate a surprisingly pristine composition. The age estimates assume 3I Atlas originated from stellar systems within 100 light-years of our current galactic position, though honestly the actual birthplace could be much farther away, given the complex orbital motions of stars over galactic timescales. Dr. Fatih Namouni from Côte d'Azur Observatory calculated that objects of this age could have originated from star-forming regions that no longer even exist, having been dispersed by galactic rotation and stellar evolution. The ancient nature of 3I Atlas gives us, well, a unique opportunity to study materials from the early solar system formation epoch, potentially preserving chemical signatures from primordial stellar nebulae that formed billions of years ago. October 30th, perihelion and beyond. October 30th, 2025 marked the closest approach of 3Y Atlas to our Sun, giving astronomers around the world optimal conditions for detailed study of this ancient interstellar visitor. Perihelion observations coordinated by Dr. Casey Lise from Johns Hopkins Applied Physics Laboratory used, honestly, just about every major ground-based observatory and space telescope to capture as much scientific data as possible. The 0.65 AU closest approach placed 3Y Atlas well within Earth's orbit, allowing for unprecedented resolution observations of an interstellar object's nucleus and its active regions. Solar heating during perihelion triggered peak cometary activity with gas production rates reaching 10 to the 28th molecules per second, and a tail stretching over 500,000 kilometers. Dr. Tony Farnham from the University of Maryland reported that high-resolution imaging revealed surface features and active jets similar to solar system comets, but, interestingly, with some unusual spatial distribution patterns. After perihelion, tracking shows that 3I Atlas will stay observable until about mid-2026 before fading beyond the detection limits of our current telescopes. The object's exit trajectory toward the Draco constellation has been calculated with precision, with a final velocity exceeding 75 kilometers per second as it leaves our solar system for good. Looking forward, future observations will focus on long-term monitoring of the tail's evolution and spectroscopic analysis of outgassing products, which will keep revealing secrets about interstellar comet formation and the chemical evolution of distant planetary systems. 3I Atlas has given astronomers an unprecedented opportunity to study pristine material from another star system, bridging billions of years and countless light-years to reach, well, our cosmic doorstep. This ancient traveler carries chemical signatures from stellar environments we may never visit, and its cometary activity proves that familiar processes are at work throughout the galaxy. As 3I Atlas continues its eternal journey beyond our solar system, it leaves behind invaluable data that expands our understanding of planetary formation all across the cosmos. Be sure to subscribe to Stellar Tech for more discoveries about our universe's most distant messengers.